So this radius over here, it is r. Okay. Okay. And the aperture is alpha on either side. Okay. And you are being asked to find out the centroid. Okay. And the author who posed this problem was very much confident that the centroid would lie outside of the, this geometry, which is the line over here. So he or she posed, already showed the centroid outside. So the way we start is with a differential line element. Okay, so we'll take this differential line dl, which is basically at any angle theta. At any angle theta, if this angle is differential increment in the theta, then this differential length is dl, which is r times d theta. Okay, and let's say if I'm interested in finding out x bar by definition of it, which is the x coordinate of the centroid. So c is basically x bar and y bar. Okay, so it is integration over the length. Okay, this is how we represent integration over the length of x dl divided by the total length. Okay, now here I already know the expression for this L, but this L also has some definition. So this L is essentially integration dl or integration r d theta, where theta lies between minus alpha and alpha. Okay, so this L would be integration r d theta minus alpha to alpha, which is twice alpha r. Okay, and similarly, the definition of y bar also goes like this. So this is 1 by L y dl. Now x at so for example, we are talking about this point over here, which is sort of in the middle of dl. Okay, so for this we may try to find out. Okay, for this dl element, everything we are doing here for this dl element. So this dl element has an x coordinate. You can think of an average x coordinate, or for that matter, the only x coordinate, because this dl is differential. Okay, so that x is over here, and this is the y. Okay, so the expression for x and y, as you have already maybe guessed, so x is going to be r times cos theta, and y is r times sine theta. Okay, so all we have to do is integrate this quantity. Let's try the x coordinate. So x bar, L times x bar, is integration over L x dl, which would be r cos theta times r d theta, and the integration goes from minus alpha to alpha. This is the expression. Okay, it's a simple expression. R is a constant over here, so it comes outside of the integration. Okay, and then there is cos theta d theta. Okay, so it's probably twice r squared sine alpha, right? Twice, so it is going to be minus sine alpha, then no, this is going to be sine alpha, then twice sine alpha. Okay, so similarly, you can find out the y coordinate, nothing different from here. And number 3, I'll go to number 3. Okay, so here, instead of a circular arc, we have a share of a pi, okay, which is basically a portion of a circular disc. Okay, again spanning over an angular aperture that goes from minus alpha to alpha. Okay, so alpha over here and alpha over here, and you are being asked to find out the centroid. Okay, R over here is the outside radius. Okay, so this is the outside radius. So if I want to identify a differential area element, okay, say at an angle of theta, okay, so if I draw a radial line, okay, and then another radial line spanning a tiny aperture d theta, okay, then I do not get, I mean, I might get an area element. Okay, so what we see is this type of a triangular area element. Okay, in some cases you'd see that people are doing sums with this strip-like or this triangle-like area element, but my suggestion would be skip this one. Okay, what you should be doing is you should take a given radius. Okay, given radius, let's say up to this much, rho, where rho lies between 0 and r. Okay, so rho lies between 0 and r. Okay, and then a differential radial distance d rho. Okay, so now we have this square sort of a area element. Okay, and we would always work with this type of an area element, where this dA is, first of all, one dimension is d rho, the other dimension being rho times d theta. Okay, so we'll always work with this differential area element, and for this one we will try to get the x and y coordinate. Okay, so as you have already maybe noticed, the x and the y coordinate is basically the weighted average. Okay, the weight being the area itself for a given area. Okay, when you are trying to find out the coordinate of the centroid. Okay, same goes for a line. Here the weight was the differential length. Here the weight would be differential area, and these are the weighted averages. Okay, so this is the x coordinate, and this much would be the y coordinate. So x, as before, is rho cos theta d theta. Sorry, not d theta. Sorry, rho cos theta, and y should be rho sin theta. Okay, and theta, as before, goes from minus alpha to alpha. Okay, so here we'll be performing area integration. So differential area being this. So for example, if I am interested in finding out the x coordinate, ax bar should be integration over a x times dA. Okay, now a is integration integration dA, which is basically double integration rho d theta d rho. Okay, now whenever we represent a double integration, okay, it is not as simple as a single integration. Okay, a double or triple integration, there are certain what should I say, norm you should be following. The thing is, this representation means the d theta integration with respect to d theta happens first, and the integration with respect to d rho happens first. Okay, so basically this representation, if I write it like this, okay, it means I'm not changing rho. So basically what you see over here, I'm not changing rho and d rho. So this portion over here, so the rho is constant. Okay, and only thing that I'm changing is gradually changing the theta. Okay, in the inner integration. So there is one outer integration and there is one inner integration. It's like summation. Okay, some of you must have had some statistics course, and you must be familiar with summation. It's like that summation. Okay, so there is an inner summation and an outer summation, but or if you are familiar with linear algebra, there also you might encounter summation. For example, if you are trying to do a matrix multiplication, a set of matrix multiplication, then you are also familiar with double summations or triple summations. Okay, so it is the inner summation or inner integration. Okay, and then once you are done integrating over this strip, okay, for a given row, you move on to the next row. Okay, and keep on doing this, thereby covering the entire area. Okay, so a lot of times, even in the textbook, you'll see they have done some sort of integration directly using a strip. Okay, I'm not going to the argument whether that would be applicable in this case or not. Okay, but my suggestion is you always stick to this tinier, double derivative sort of differential area. Okay, and let the math turn out to be the way it should. Okay, otherwise the chance of having mistake is huge. Okay, I'll tell you the cases where you will be encountering mistakes. Okay, because I have seen those type of mistakes over the years. Now, this is also how you put the limits. This is also how you put the limits. So you see rho d theta over here. Okay, so since theta is the inner integration, I should be putting the limits of theta. Okay, first. So it would be from minus alpha to alpha, and since the outer integration, so you can put a bracket if that what is convenient for you. And this is the integration we would do first, and then there is d rho. Okay, so in this case, the limits on rho are from 0 to r. Okay, this is the integration. So can you solve this expression? Can you solve this expression for a? Can one of you tell me the final expression for this one?
R squared.
Sorry? R squared?
Alpha.
R squared alpha.
R square.
R squared alpha. R squared alpha. Now alpha by 2.
Yes, sir. R square alpha.
R square.
R squared alpha. Yes, yes. Correct. Okay. So for example, if I had taken alpha equal pi, okay, what expression should I get?
Pi r square.
Pi r squared being the
Circle.
total area of the circle. Total area of the circle. Okay. Okay. Achha. Let's now. So similarly, we can use it for x as well. Okay. So only thing is I should be substituting rho cos theta over here. Achha. So I'll also do the other type of integration where the representation is with the integration over okay, rho, integration over rho is the first. So again I'll do this then rho d rho times d theta. Okay, so so in this case the limits on rho should apply first, 0 to r, and then there is minus alpha to alpha. The final expression is going to be the same. Okay, actually even in this representation I can switch the order. I can switch the order of integration. Okay. Why can I change the order? In this case, it's because you see the limits on integration of rho and theta, they are independent of one another. It means that the limits of integration on, for example, theta, okay, they are independent of rho, and limits on integration on rho, let's say, they are independent of theta. In a situation like that, you know, the integration could be, you can switch the order of integration. Okay, so in matrix multiplication, you can often switch the order of summation. It's because the limits are independent of one another. The limits on summation may be running from 1 to 3. Okay, so that those limits are independent of one another. Now I'll go to one more case which is not shown here, but I'll anyway go there. Okay, so imagine you are trying to find out the centroid of this rectangle, and it is obvious the centroid of the rectangle lies exactly in the middle. Okay, but let's not make any assumption. Let's go by the standard way. So this is my differential area, dx dy. Okay, and x goes from x1 to x2, and y goes from y1 to y2. And no matter which integration am I doing, whether integration x dA or y dA or simply integration dA. Okay, so in this case, let's say if I try to do this, a times x bar. Okay, so let's say I'm writing it like this, dx dy, x times dx dy. Okay, now in this case, so the limits on x are x1 to x2, because this is my inner integration, and limits on y are y1, y2. Okay, the thing is, as I mentioned earlier, when I'm doing the inner integration, I'm keeping the outer integration fixed. It means I'm keeping y fixed. Okay, this integration is happening over this strip. It's happening over this strip. Okay, so we can always treat y as a constant. Okay, so in other ways, it is like y1, y2. Okay, dy. I'll not write it like that. So I need to integrate this quantity, which would turn out to be half of x2 squared minus x1 squared times dy. Okay, and then when I do the next step, it becomes x2 squared minus x1 squared times y2 minus y1. Okay, now I can also write it to be x1 x2 integration y1 y2. Okay, and x dy dx. Okay, now this is simply doing like this, like integration over rho first and then with respect to theta first. Okay, so I'm trying to do this integration first. Okay, so as I mentioned, if I'm doing the inner integration with respect to y, I'm keeping x constant. Okay, so x is a constant. I'm just performing integration, taking differential y elements, okay, over this strip. Okay, so what I can do is I can treat x as a constant. Okay, so it turns out to be x1 x2, so x dy times x dx, it should be x dx, y2 minus y1. Okay, and in the end it is again when we are done integrating with respect to y. Okay, since we are done integrating with respect to y, so the y part is no longer there. So now the integration, now for this integration, this y2 minus y1 times dx, okay, this basically is y2 minus y1 times dx is basically this area. Okay, now I'm doing the integration with respect to x over this element. Okay, so this is going to be, so again y can be treated as a constant. The values of y are constant. In this case, the values of y are constant. Okay, so this is a special case. This rectangle is a special case. Okay, where after integrating with respect to y, after integrating with respect to the inner variable, okay, you have got constants in your hand. That is not always the case. Okay, this y1 and y2 are in general functions of x. Okay, we'll see such examples. Okay, in this case, these functions are basically constants, and so in this case, what we will get again. Of course, we will get what in the expression we had earlier. There is no doubt in that. Okay, because both integrations are correct. Okay, so you'll obviously get the same expression. There is no doubt in that. Okay, but with just like the previous case, the limits on x being independent of limits on y, and limits on y being independent of x. Okay, just like the previous case where the limits on rho were independent of theta and limits on theta were independent of rho. Okay, what we can do is we can write this expression or any integration, okay, with respect to in general, okay, any integration in this case. Okay, let's say some function of it should not be a combined function of x and y. So in this case, let's say x dx and dy. Okay, so limits are let's say x1 x2 y1 y2. We can write it to be integration y1 y2. Oh, no, I should clear this space actually. We can write it to be this integration I over here. Let's say integration x dx dy. Okay, ranging from x1 to x2 and ranging from y1 to y2 can be written as this product of two integrations y1 y2 and x1 x2 x dx. Okay, you can take all the terms related to x and put it in the integration with respect to x, and all the terms with respect to y and put it in an integration with respect to y. Okay, and there are two separate definite integrals, okay, which can be multiplied. Two separate definite integrals which can be multiplied to give you the final expression, and that can only be done when the limits are independent of one another. Okay, in a rectangular coordinate system, when you have a rectangle, okay, you can do such an operation. When you are integrating within a rectangle, you can do such operation. But if you are using r theta coordinate system or a polar coordinate system, you can do such an operation when you have in hand, a portion of a circle, a hollow circle, anything. Okay, so basically a circular segment or a hollow circular segment is equivalent to rectangle. Basically, you can have r1 and r2. So this one is r1 and this one is r2, and this angle is theta 1 and this angle is theta 2. Okay, so in r theta coordinate system, it is that circular segment, the portion of that circle is essentially a rectangle in r theta coordinate system. Okay, and the limits being independent, you can represent any integration just like this. Take the y dependent terms on one side, the x dependent terms on one side. There will be two definite integrals and simply multiply them. Okay, now we'll move on to the next problem. Okay, এই কথা যেগুলো বললাম এগুলো কি বোঝা গেছে সবার? বোঝা গেছে? আচ্ছা, এটা কি খুব obvious যে পার্টটা বললাম? Is it really obvious? Then we can skip actually this sort of thing.
স্যার অ্যাকচুয়ালি আমাদের মধ্যে আধের জন থেকে বেশি জন ডাবল ইন্টিগ্রালস করেনি স্যার এখন অবধি।
স্যার আরেকটা ব্যাপার, মানে এই ডাবল ইন্টিগ্রালে আপনার মানে এই মানে যে সুইচ করলেন অর্ডারটা, এটা কি অলওয়েজ হয়? মানে এমন কোনো কেস দেখান যে যেখানে হয় না বা কিছু?
That's what I'm planning. একটা দেখো, একটা যেটা বললাম যে if we start with this expression, after that also we can switch the order when if we have independent limits. Okay, but and eventually we can represent that as a product of two definite integrals, two separate definite integrals, one with respect to x, another one with respect to y. Okay, and that can only be done on a rectangle, be it in a xy coordinate system or in a r theta coordinate system. Obviously, the rectangle in r theta coordinate system doesn't look like a rectangle in a physical coordinate system, because physical coordinate system is Cartesian. So so I'm just, the next problem I'm about to do, okay, it is about the most general case where you cannot do that. Okay, but actually I'll not do the question number 4. I have a separate preference with a different type of expression. It also looks very symmetric, hence a favorite problem of mine. I still want to come back to this circular portion. I'll tell you why. Delete hobe na? Okay, so the problem I'm about to do is much similar to problem number 4. So what you have here is x and y. Okay, and a very symmetric, very nice looking area in hand. The equation of this line is x equals y. Equation of this curve is y equal root x, and equation of this curve y equals x squared. So in this area, okay, I'm about to perform an integration. Okay, so let's take a differential area, and you cannot be wrong by taking this tiny differential area. Okay, so this is my differential area, dx dy dA. Okay, now now the thing is, let's say I'm interested in finding out integration x bar a, which is basically integrated over area x dA. When I'm mentioning it is an integration over area, I'm showing a single integration. Okay, as if I have some means to directly perform an integration over an area. Because I don't, hence I have to put dx dy, substituting dA, and essentially therefore I'll have to use double integration. Again, in this representation, since I have put x first, I can only perform the x integration inside. So again, the integrand is x. The integrand would not change, okay, in either representation. So now that the first, so the last limits, okay, the last two limits. Can you tell me what are the maximum and minimum values of x and y? It is 0, 0 and 1, 1. Okay. So the limits on y are limits on y are 0 and 1. Okay. But the limits on x are not 0 and 1. You see this inner integration over here, that I'm performing at a constant y. Okay, that means that integration is happening, okay, within this strip of thickness dy, okay. So y is constant but x is not. Okay, obviously, otherwise there would be no integration if x were a constant. But then the limits on x are also not 0 and 1. The limits on x are actually dependent on y. If y indeed was 1, okay, both the limits on x would be 1 and 1. If y indeed was 0, both the limits on x would be 0 and 0. But in between, the limits on x are different. Okay. For example, this one I would call x1 and this one I would call x2. The lower value I will call x1 and the upper value I would call x2. And as you can see, they are functions of y. Okay. And this is the general representation of any area integral. Okay. Irrespective of the integrand. Okay. This is the most general representation. Okay. Now, what are x1 and x2 in this case? It says y equals
so y square and root under y.
Yeah. Yes. So it says the equation of this line says y is square root of x. So x is y squared. So x1 is y squared. And then this equation says y equals x squared. So x is square root of y. So the first integration should be, okay, so this all is there, and then it should be half of x2 squared minus x1 squared. Again, remember when you are integrating in this strip, x is changing, y is not. So even to this integration, these two are like two constant limits. Okay. So you treat them as any normal limits. Okay, like in a single integration. Okay. Only when they appear in the second integration, when you are done integrating within this strip, okay, then you actually use their functional form. Okay. So x1 squared and x2 squared. Now how much is x2 squared? It is y. How much is x1 squared? Y to the power 4. Now it may be difficult for you to think of a limit where certain quantity goes from to the power 4 to the power 1. Okay. But you need to understand all the values that I'm talking about are less than 1. Hence the quantities with lower power are actually higher value. Okay. For example, if y is 0.5, so this quantity is 0.5 and this quantity is 0.0625. Okay, and that's where the maximum span is, by the way. So I guess from this point onwards you can perform the integration. Okay, so from 0 to 1, half of y minus y to the power 4 dy, and this is what you can easily do. Okay.
Yes, sir.
Yes.
Sir, বলছে যে এখানে x is equal to y এর কি ফাংশন হলো? মানে ওই মাঝখানের লাইনটা
মানে সেকেন্ড লাইনটা তো
হ্যাঁ মানে সিমেট্রি যেটা হচ্ছে
no, I'm not using any form of symmetry because the symmetry is also about not either or x or y axis. It is about an axis x equals y. So let's not go into the symmetry part. The symmetry part is what I like about this problem, but I'm not using anywhere. Okay. So what you see here is the limits on x. Is this part understandable? That limits on x are not independent, unlike the rectangle, unlike the circular segment. Okay, the limits on x are actually dependent on y. Can you see that? Is that clear?
Yes, sir.
The limits on x, because when you fix a particular y, x can only change between these two values. Okay, from this curve to this curve. So whatever are the equations of these two curves, okay, written like this as x equals function of y, okay, those are going to be the limits on x. Okay, and since when you are integrating with respect to x, just do it like a normal integration. How would you treat like a normal definite integral? It would be like half of x2 squared minus x1 squared. It's just that, see, this x2 and x1 are constants. They are limits. They are fixed values when you are at a given y. Only when you change y. When are you changing y? In the outer integration. When you appear at the outer integration. Before that, these two are constant. Only when you appear at the second integration, okay, that outer integration, that's when you write their functional form. Okay, before that, treat them as just like numbers. Okay, So, so you wrote the expression the way it should be, half of x2 squared minus x1 squared, the obvious one, and then you substitute their expressions. Okay, because you see, if you're done integrating within this strip, you would move on to the next strip, right? And before that, you had done the integration in the previous strip. And each of these strips, what has changed? Y has changed. And because the limits on Ax are also functions of Y, those limits have changed. So write them as functions of Y, the limits on X as functions of Y, okay? And then perform the integration with respect to Y. Now, again, I have written it like this, okay? I could have also written it like this. I could have written x dy dx, and it would still be the same expression, totally correct, no issue in that. But the limits on y are going to be functions of x. So again, y1 is here, and there it will be y2. Okay, so y2 is square root of x, and y1 is x squared. So it is square root of. So this is the expression. Now you see, in the inner integration, because I am now performing integration within this strip, for me x would be constant. This is constant. Okay. So what is changing? Y is changing. Since x is a constant, it can come out of the integration, only the inner integration. Okay. So x comes out over here, and then you are integrating with respect to y. Okay, which would be square root of x minus x squared. Okay, and then dx. Okay, if you perform this integration 0 to 1, okay, x times square root of x minus x squared dx. Okay, now I need you to evaluate the first integration and the second integration. Okay, and check if you get the same expression. Okay, but you will get the same expression, I know. Okay, but you can do it later. Okay, now just see one thing. I changed the order of integration. Okay, but I could not keep the same sort of limits. If I were to keep the same sort of limit, here the outer limit should be square of y and square root of y, and the inner limit should be 0 and 1. But that has changed. Okay, I cannot switch the order keeping the limit same. Okay, this is not possible when the limits are functions of the limits on the inner integration are functions of the outer the variable of the outer integration. Okay. So that is the difference over here. You see, earlier the limits on y were 0 and 1. Now they have become square root of x and x squared. Okay, earlier the limits on x were square of y and square root of y. Now the limits have become 0 and 1. Okay, such was not the case over here. I could switch the order, okay, keeping the limit same. Okay, and I could actually represent them as products of two separate definite integrals, which I cannot do over here. Okay, so so you can decide which integration of these two. This should be not xj but x bar times a. So doing the x integration first or the y integration first, which is more convenient to you? Okay, and in which case maybe you can use different order of integration to calculate the two different values. Maybe for this case doing the y integration first helps. Maybe for this case doing the x integration first helps. Okay, you get to decide. Okay, as long as you are consistent. Okay, and many a times I would notice people doing this. They would simply take this strip-like element, okay, and call their dA to be dA to be y2 minus y1 times dx. Okay, so this is dx, and this lower curve is y1, the upper curve is y2. Okay, value at the given x. Actually the value of this lower curve at the given x is y1, value of the upper curve is y2. and that way they would take the dA. Okay, and it is quite useful when you are trying to get x bar times a. Okay, because in that case x is not changing. Okay, on this entire differential area the x is not changing. Okay, so doing this would not be much of inconsistent. Okay, but when you try to do y bar times a equals y dA, then the question remains whether you take y1 or y2. And what people intuitively do is they take y1 plus y2 by 2 dA, which is fine, which will also give you the correct result. Okay, but only when you are taking a rectangular sort of differential area. In case you are taking a triangular sort of differential area, okay, if you are taking this triangular sort of differential area, where this triangle is essentially the area of this differential triangle would be r times d theta by 2 times r. So this is the area of this triangle, and you take somewhere in the middle, okay, as the centroid of this triangle. But the thing is, the triangle centroid is not halfway between its base and vertex. Okay, unlike a rectangle. For a rectangle, the centroid lies exactly in the middle. Okay, but for a triangle, the distance would be 2/3 from the vertex. Okay, so if the distance between the vertex and the base is r, it would be 2/3 r. Okay, and if you look at the problem number 2 over here, that actually is asking you to prove that. Okay, so depending on what type of differential area you are taking, you should be doing all sorts of manipulations. Okay, but again, taking this y1 plus y2 by 2, okay, will only work, okay, for a rectangular element when you are trying to get the centroid. When you are trying to get the moment of inertia, you are actually not integrating y dA, but you are trying to get y squared dA. Okay, now the average value of y squared for a rectangle is not half away. Okay, it's not actually half away, it's actually further than that. Okay, integration y squared dA, and that distance is called something called the radius of gyration. We'll come to that. Okay, and because of that, taking y1 plus y2 by 2 would be incorrect. What would be correct and always correct would be taking a differential area which looks like this, double differential. Okay, and performing a double integration. Many of you would be scared of double integrations, but as long as you are consistent, there is absolutely no reason to be confused. Okay, basically there are two independent variables. Okay, but for a generic geometry, generic shape, okay, the limits on the inner integration, so there is one inner integration and one outer integration, just to be frank, that's something you need to keep in mind. Okay, and based on what you write, you may choose to write dx dy or dy dx, and as you practice more and more problems, you know when to take which one first. Okay, and once you take one of them first, the other one second, for the inner integration, the limits on the independent variable, okay, or the limits of the integration should be a function of the outer variable, and the limits on the outer variable or the limits on the outer definite integral should be constants. Okay, so as long as if you keep that thing in mind, and when you are performing the inner integration, the variable from the outer integration is actually constant, because you are performing the integration on that strip. For example, the outer integration is with respect to x, so in inner integration you are only performing integration with respect to y, so x is a constant. So even if there is a x, don't be scared. Okay, simply put it outside of the inner integration. Okay, so it's simple. Okay, and it will always yield correct result. Okay, so my suggestion is stick to that. If you have further problem, let me know. Any question regarding centroid? আমার কথা শোনা যাচ্ছে?
হ্যাঁ স্যার।
হ্যাঁ স্যার।
আমি ধরে নিচ্ছি কোনো ইস্যু নেই। We'll quickly move on to Papa's theorem. Okay, and if you have already read about it, you know what it is. Okay, and you know that while mentioning that it gives you the surface area of revolution or volume of revolution, you need to mention that only that thing only happens for a non-intersecting curve or a non-intersecting surface. Okay, it can be a closed curve, it can be an open curve. Okay, what I'm trying to say here is when you are using Papa's theorem, it equally applies in giving you this a toroidal surface, the surface of a tube. Okay, or if I instead choose to have an open curve and made a surface about it. Okay. For example, an arbitrary open curve and make a surface through that. It works in either case. Okay, no issues. But what it cannot do is this curve cannot intersect this axis. Okay, because then your surface area of revolution is something like this, undefined sort of. So it should not be a non-physical case. Okay, so so that thing goes into your definition. Whenever you are asked to give the definition of Papa's theorem, keep that in mind. Okay, and the proof is also very simple, so I don't think that should be a problem. But what could be a problem, in my opinion, when I ask you to give both the surface area of revolution and volume of revolution. So I'll quickly move into one such example. Okay. Let's take the simplest case. Let's take question number 9. What you have here, you don't need the 3D representation. You only need this triangle, right? So this is the triangle, okay, with a height of 12 mm and the width also 12 mm. Right angle triangle, no issues. 8 mm away, okay. And to get the volume of revolution, you need the area times so it should be rotated about z axis. Okay, so y axis is inside the paper. Okay, so you need a x bar and the angle. So in this case the angle is phi. Okay, so you can calculate the area centroid. I think by this time you already know this. It is actually it would be 2/3 away from the vertex. Okay, the centroid would be 2/3 away from the vertex. But if you really want to calculate it, since I only need x bar and not y bar, I can take, and I repeatedly ask you not to use, but I am still using, just to make the process quicker, nothing else. Okay. So for any given x, okay, the differential area is so this angle is 45 degrees, right? So basically equation of this line is y equals x, and so basically this y is also x. Okay, so the differential area dA is x dx. It should have been y dx, but y is also x, so x dx. And so ax bar is integration xd, of course, but that is also x dx. Okay, actually x times x dx, differential area dA, and ax goes from 8 to 20. No, sorry, I made a mistake. The Ax goes from, sorry, Ax goes from 0 to 12. I'm simply in my mind shifting the coordinate system over here. Okay. And then later I'll add 8 mm to the centroid. Okay. So integration x squared d. Area is something we already know. It is half of 12 times 12. So 72 mm squared. Okay. And now we are performing this integration. Okay. So it is 1/3 into 12 cube millimeter cube. Okay. And that you divide with 72. Okay. So you actually don't need x bar. Okay. You can simply, you don't actually need this quantity also. You don't need this. You simply calculate the Ax bar. Okay. So okay, and simply multiply with pi. Okay, that should give you the volume area, volume of revolution. Okay, so this quantity you can calculate, and this is fine. Okay, now some of you, what you do is, you know this quantity. You know this quantity x bar is two-third of this distance, which is 8 mm. Okay. Achha, by the way, this thing is this plus whatever the area is, 72 into 8 additional, because of this offset. Achha. Some of you already know that this x bar is two-third away from the vertex, which is fine. Knowing is fine, and for a simple geometry such as triangle, you probably should be allowed to use the expression. It is fine, but keep that in mind. That is the exponent of the centroid of the area. Okay, and that only applies to volume of revolution. If I have also asked you to give me the area of revolution, okay, only the area of revolution, not the side surfaces, okay, that you can add later. But if I have asked you to give me the area of revolution, you are supposed to give me, you're supposed to take the centroid of the boundary, which comprises of 3 sides. Okay. So basically, integration, you're supposed to take Lx bar. Okay. So it is going to be pi times Lx bar, and Lx bar is integration x dl, going from 0 to L. It can be divided into 0 to, so I made a mistake. It should be L1, sorry, not L1. This should be L. So when you are splitting that, it should be L1 x dl plus L2 x dl plus L3 x dl. Okay. Now, again, that is also intuitive. Okay. For L1, x is kind of constant. So it is 20 times L1, which is 12. For L2 and L3, it can be easily understood that the centroid of these two lines lies in the middle. So it is going to be 8 plus 6, 14. So it is going to be, these two combined, it is going to be 14 times. Now this length is 12, and this thing is 12 root 2. The abscissa is 12 root 2. Sorry, not abscissa. The hypotenuse is 12 root 2. Okay, so if you do that, okay, that gives you Lx bar, and it is not equal to L times the x bar you got from the area integral. Okay, you can check the two centroids are going to be different. For surface area of revolution, use the centroid of the path or the boundary or the curve. For volume of revolution, I mean, I'm mentioning it as use, but that is how it should be. Okay, use the centroid of the area. Okay, so I guess that way you would be correct. One more thing is with composite areas. So if you look at the figure, composite areas, or for that matter composite curves or composite curves and composite areas, let's say. So for example, question number 6. Okay, so it can be thought of so you can imagine this one is A1, this rectangle is A1, this triangle is A2, and this circle is A3. Now the area in hand is A1 plus A2 minus A3. Okay, so if I'm trying to find out the centroid or the moment of inertia or any other quantity, okay, and I'm performing an area integration, whatever function of x and y over a dA, it is actually f of x and y dA over a1 plus a3, or I shouldn't be writing it like this, a1 plus that over a3 minus that same quantity over a2. Now in that way the area becomes a1 plus a2 minus a3. Okay, where you are that integrand f of xy equals 1 when I'm trying to evaluate the area. Okay, and let's say I'm interested in finding out the centroid. So for this it should be equal to x.
স্যার আপনি এখানে a2 টাকে মাইনাস কেন করলেন?
a2 টাকে মাইনাস কেন করলাম? দেখো একটা সার্কুলার হলো কাটা রয়েছে এখানে, সেই জন্য মাইনাস।
স্যার সেটা তো আপনি a3 ধরেছিলেন না?
a3 ধরেছিলাম, হ্যাঁ a3 ধরেছিলাম, তাহলে ওটা লেখাটা ভুল হয়েছে। ঠিক আছে, সো যখন আমি মানে এরিয়া ক্যালকুলেট করছি, the integrand is 1. When I'm trying to get the centroid, my integrand should be x. Okay, ever when I'm doing so for example, if I do this x dA, it is going to be x dA over a1, or for that matter summation over I. Okay, I'm assuming that all signs are plus. Okay, now I mean if it is minus, just think of that dA is negative. Okay, if it is minus, just think of that dA is negative. So I equal 1 to n integration x dA, ai over integration over ai, which is basically x bar I times ai, where x bar I is basically the centroid of ai. Okay, so I goes from 1 to n. Okay, so we know that the net x bar times a is integration is this quantity. Okay, so this quantity is basically summation over xi bar ai over I. Okay, and this a also is summation over I ai. Okay, assuming all are positive quantities, all areas are addition. Okay, and then if something is subtraction, then assume this dA to be negative. Okay, or that corresponding ai to be negative. Okay, So therefore x bar is summation over xi bar ai divided by summation over ai. Okay, that is the formula for the composite area, and you can replace A's with L's to get the the centroid of a composite boundary or a composite curve. Okay. So in this case, it is going to be the x bar, net x bar for this geometry is going to be a1 x1 bar plus a2 x2 bar minus a3 x3 bar by a1 plus a2 minus a3. Now you can very easily calculate these areas. You know the formula for a triangle, and you of course know the formula for a rectangle and also for a circle. So you know AIs. Do you know XIs? X bar I's? You also do. For rectangle, it would be in the middle, 200 mm. For this triangle, it would be 200 plus 200 plus 150 by 3. It would be closer to the side than a vertex. Okay. So 150 by 3. So 400 plus 50, 450. For the circle also, it is 200. And similarly, you can find out the y coordinates. For rectangle and circle, they are both going to be 125. Whereas for the triangle, it is going to be 1/3 away from the base or 2/3 away from the vertex. So it is going to be 250 by 3. Okay, just substitute those quantities and you'll have your x bar and y bar. So that way you can do composite geometries. Okay. Any question regarding composite geometries? Anyone? বোঝা গেল এই পার্টটা?
হ্যাঁ স্যার,
এটা করা যাবে তো এই প্রবলেমগুলো? আচ্ছা, we'll now dive into solving moments of inertia. Okay, and there is not much to cover except for the theory of it, because all the tricks related to integration, okay, all the tricks related to composite geometry have been covered so far. Okay, so we are only left with the definition of moment of inertia. Now, before going into moments of inertia, a little background. You can always figure out what is the importance of a centroid. One of the importance is, a lot of times you'd be calculating the moments of inertia with respect to the centroidal coordinate system. Okay, in mechanical engineering. Okay, for example, if you're working with beams, and first of all, why do you need moments of inertia? Okay, that also you need for beams sort of structures. Okay, and the geometric part of the resistance in bending, okay, in beams and columns are dependent on the quantity called moments of inertia. Okay, so so the thing is moment of inertia about the centroidal coordinate system is what we require. Okay, so you should be able to calculate both the centroid and the moment of inertia. So we'll look into the moments of inertia. Okay, so these are the basic geometries: the triangle, the rectangle, and the circle. Okay, and even, let's say if you have just a generic geometry bounded by two curves, we follow the same rule. So I'll simply give you the definitions. I think that should be enough. And the rules or the methods or the tricks that I have mentioned are same as before. Okay, so no change there. So let's say you have a generic geometry. Again, let's take the example. This one is x square and this one is square root of x. This is 1 and this is 0. Okay, and you are integrating in ixx, and you must be familiar with mass moment of inertia. Just keep in mind, this is not mass moment of inertia. Okay, this is the moment of inertia of the area. Okay, and this is the distance from. So this is the measures the distance from x-axis. Hence, you take the y squared over dA, y squared over area. Okay. So you can do both ways. For example, in order to calculate this, you can take an entire strip, okay, which has a constant y, and can perform this quantity. It is fine, but my suggestion would be stick to the basic double differential square shaped area, differential area. Okay, just stick to that. So and you cannot use, let's say, this type of a differential area to get Ixx, because y itself is not a constant over here, and taking y1 plus y2 by 2 would be incorrect. Okay. Because then you are treating this total geometry to be a composite geometry of several rectangles. But then for rectangles, there is something called the radius of gyration, which is basically this by area. Okay. Now imagine there is one area which is very close to x-axis. Now the same area oriented like this. So this is x. Okay. This time mostly spans away from x-axis. In the second configuration, it will have more moment of inertia about x-axis. Okay. So that's where the radius of gyration comes. Okay. In accordance with the area, you know how much it spans further from x-axis. The area, along with its net area, you know what is the span further from x-axis. That can be known from kxx. Okay. And if we go by literal definition, kxx means that instead of your area having a continuous span, okay, if it were to be concentrated at a point, how far that point should be from x-axis to give you the same area moment of inertia, okay, is what is known as the radius of gyration. That is what the literal definition means. If the area were not to be distributed, but to be concentrated at a point and to be at a certain distance from x-axis, then how much further should it be to give you the same moment of inertia is what is known as radius of gyration. Now, this definition is vague. I agree. It's an abstract definition, abstract mathematical definition. Just like the radius of gyration, when you are talking about mass moment of inertia. Okay. Let's say about x-axis, you are trying to get the mass moment of inertia, okay, of a rigid body. Let's say it is performing rotation, so you need mass moment of inertia to calculate angular acceleration, apply some torque, okay, and you need to get the alpha, okay. So you need the Ixx, so you can divide the torque and get your alpha, the angular acceleration. So so you take the differential m, okay, and try to get the distance from x-axis. Let's call it it would be a combination of y and z, so let's call it r. Okay, so then you do this r square dm over m, okay, and then you call m times kxx, okay, where kxx is the radius of gyration about x-axis, which again means given the mass, how much further is the geometry spanning away from x-axis, okay, or how much it is utilizing the space to increase the mass moment of inertia. Okay, there saying this would not be, you know, so much of an abstract for you, that instead of having the mass distributed over the geometry, if it were to be concentrated on a particle or at a point and then being situated at a distance of kxx and still producing the same mass moment of inertia, then kxx should be the radius of gyration. Okay. Now somehow the thought of mass being concentrated at a location Okay, does seem a little less impractical than the area being concentrated at a point. But the thing is, both the definitions are abstract. Okay, and I mean, you shouldn't take them literally. Okay, they practically they mean how much the area is being distributed further from an axis. Okay, the area can be distributed in different ways with the same area. Okay, so that's it. Okay, with the radius of gyration. So that being said, for a rectangle, if I take the axis from its base, now it would matter where do I take the axis. Then the radius of gyration is two-thirds of its height away from that axis. Okay, possibly. I'm not sure. You should check, but it's not in the middle, unlike the centroid case. Hence, for a mass moment of inertia, taking dA to be y1 plus y2 by 2 is incorrect. Okay, so stick to the tinier differential area, or if you are really willing to go with a strip-like area, then think of what quantity you are trying to evaluate. If it is Ixx, then you are integrating y squared dA. Okay, so then therefore y is something that needs to be constant on that strip-like area. So you should be taking this type of a strip. Okay, if you are not comfortable integrating in that strip, and you will encounter such situations if you practice enough problems, okay, then skip taking any type of a strip. Okay, simply take the tinier differential area, the most absolute differential area, okay, involving double derivative. Okay, and perform double integration. So that way you can calculate Ixx, and similarly Iyy is called the area moment of inertia about x-axis. So it is again, as the differential should be this quantity. J is called the polar moment of inertia, which is r squared dA. So you basically take the moment of inertia with respect to the origin. Okay, now that origin obviously depends on where you take your coordinate system. If this is your coordinate system, then that is the origin. O prime is your origin instead of O. So therefore if this quantity is x squared plus y squared times dA. Okay, so basically it is Iyy plus Ixx in that given coordinate system. Sum of these two quantities in that given coordinate system. Okay. Now again, I'm only going with the theories of it. I'm not doing any problem, because how you should be able to solve any of those problems, I have already discussed that. Now, one more thing with the moment of inertia, actually a couple of things. One is the product of inertia. So that is also for definition, Ixy. So for a given area, I would take the differential area, I would take the y coordinate, I would take the x coordinate of the differential area, and this thing is defined as xy dA. Okay, and this involves both x and y. Okay, and since it does, you cannot take any of the strips. Okay, you should be going with, so none of them are constants, so you should be going with the tinier differential area. Okay. Why do we need Ixy? We need Ixy. So in a minute we'll be discussing about something called parallel axis theorem. Okay, I'll come to that, which basically deals with, if I have moment of inertia about xy, how do I get moment of inertia about x prime and y prime when these x prime and y prime pass through the centroid? Just keep that in mind. I'll come to that in a minute. But what we see is, in a parallel set of coordinate system, I'm about to evaluate, given Ixx and Iyy, I'm about to get Iyy prime, Iy prime y prime, and Ix prime x prime. Okay. I can get that using parallel axis theorem. I'll come to that in a minute. But before going into that, okay, this thing is not in your syllabus. You will not have to solve any problem with this. But imagine at the same location, the two coordinate system that I'm talking about are at an angle. There is no translation but a rotation of coordinate systems. Then how to get the moments of inertia about this rotated coordinate system? That's where this quantity becomes important. Okay. Then we need something called Mohr Circle. People who are interested, go through the book and also search about it. Okay. This actually is an universal way of getting coordinate transformation in terms of rotation for quantities which are like tensors. For example, the I tensor can be populated with IXX, IYY, IXX, IXY, IYX, and apparently IYX by definition is also IXY. You see, integration x dy is integration yx dA also. Xy dA is also yx dA. And then IYY. Okay. Now this is with area moment of inertia. With mass moment of inertia, that would be 3D. Okay, so it would be involving z coordinate as well. And also there is something called stress, okay, represented with Greek symbol sigma, and typically thought of as the force per unit area, with the most general case a cylinder having been pulled by a force F over its cross-section area A. But that is not the only sort of stress that is there. Okay. Instead of assuming a cylinder, imagine a parallelepiped, and it could be stressed in all the three directions. And it could not just be under normal stress, but also shear stresses, 2 in each plane. So there are total 9 components of stress. Okay, and stress kind of looks like a matrix. Okay, so sigma xx, sigma xy, sigma xz, sigma yy, sigma zz, sigma yz. Okay, and symmetry. Okay, symmetric bottom triangle. So even for this one, okay, actually the 2D version of it, okay, and this 2D version of area moment of inertia. Area moment of inertia is indeed 2D, and then the 2D version of mass moment of inertia. Everywhere you can use Mohr circle to do such coordinate transformation. Okay, so for that you need IXY. Okay, and now to parallel axis theorem. So let's say this much is the y bar and this much is the x bar. লোক সংখ্যা কমে 63 হয়ে গেছে। So this much is x bar and this much is y bar. And let's say this is the differential area. So this distance is dy prime. No, sorry, not dy prime. This is y prime. And this distance is x prime. Differential area, let it be dA. Okay. So we see that y is y prime plus y bar. And let's say I'm trying to evaluate IXX. So I'll be doing integration over a y squared dA. Okay. Now that would be y prime squared plus twice y bar y prime plus y bar squared times dA. Now the first term will give you integration y prime squared dA over A. This is nothing but I x prime x prime. The next quantity, I'll come to that in a minute, is twice y bar integration over A y prime dA. Okay. And the third quantity is, you see y bar is a constant, so y bar squared integration dA, which is basically A. Now let's look at the second term. This quantity is total area times y bar prime. What is the meaning of the term y bar prime? It is the coordinate, y coordinate of the centroid measured with respect to the centroid. Okay. You see, centroid is in the middle. Some y bar would be positive and some y bar would be negative. Okay. When you take the average of that, weighted average of that, you get the coordinate of the centroid with respect to itself, which means this quantity is 0. Okay, which means we are left with this expression. Okay, so as I mentioned earlier, in order to get the moments of inertia with respect to the centroid, you need the coordinate of the centroid. Okay. So the second term drops out. This is the final expression for the parallel axis theorem, and this is also an universal expression in terms of area moment of inertia, mass moment of inertia, and even the product moment of inertia. Okay, and the polar moment of inertia. Okay. So I'm not going to derive the rest of the rest of the four. So you can do it on your own. Okay, and I think what have been discussed so far, with that you can do all the problems in the problem sheet or all the problems in your paper.
স্যার বলছি যে স্যার এই এতগুলো হবে না স্যার, এমনি এই সপ্তাহে সব অ্যাসাইনমেন্ট দিচ্ছে অন্যান্য সাবজেক্ট। তো আপনি কি তাহলে ফাইনাল, মানে আপনিও তাহলে ফাইনাল অ্যাসাইনমেন্টটা কি দেবেন?
আমার মনে হয় এই সেন্ট্রয়েডের চ্যাপ্টারটা তো হয়েই যাবে। আমরা যদি আজকের ক্লাসটা স্টপ করি এখানে, ঠিক আছে, ডাইনামিক্স যদি আমরা নেক্সট ক্লাসে করি, ঠিক আছে, নেক্সট ওয়েডনেসডে করি, তার মধ্যেই 10-11টা প্রবলেম হবে না? কটা প্রবলেম আছে?
20টা মতন আছে ওখানে।
20টা মতো আছে, 19টা প্রবলেম আছে। But apart from this last few problems in moments of inertia, the initial problems are very easy. Okay, actually these two have been already solved. The first three have been already solved. Okay.
এই জন্য না, আসলে স্যার এই সপ্তাহে আমাদের আরো 4টে অ্যাসাইনমেন্ট রয়েছে এই 3-4 দিনের মধ্যে, গ্যাপে গ্যাপে, প্লাস ভাইভাও আছে, সেই জন্যই আর কি একটু সমস্যা হয়ে যাচ্ছে।
স্যার সব দিক থেকে একবারে বাস পড়ছে স্যার,
মানে এতদিন আপনার গোটা সব প্রবলেম মিলিয়ে যা করেছি সেইটাই আবার সেম 3-4 দিনের মধ্যে আবার করতে হবে, অত অ্যামাউন্টেরই কাজ।
আচ্ছা ঠিক আছে, এক কাজ করো, ওয়েডনেসডে আমরা ডাইনামিক্সের প্রবলেম করব, ঠিক আছে?
হ্যাঁ,
কিন্তু তোমরা এই যে অ্যাসাইনমেন্টটা,
হ্যাঁ
and properties of surface, আমি জানি না ফ্রিকশন তোমরা করে ফেলেছো না?
হ্যাঁ, ফ্রিকশন করে ফেলেছি।
ওকে, friction and properties of surface would be evaluated together, ঠিক আছে? and friction and properties of surface, এই দুটো আমরা মানে বাই থার্সডে ইভিনিং আমাকে এই দুটো সাবমিট করো, তাহলে ঠিক আছে?
বাই থার্সডে ইভিনিং?
হ্যাঁ,
মানে প্রপার্টিজ অফ সারফেস বলতে আপনার শীট নাম্বার কত?
এই শীটটা বোধহয় আমি শেয়ার করেছি গত সপ্তাহেই, শেয়ার করেছি।
শীট 5, আচ্ছা এটা শীট 5 তো?
হ্যাঁ, এটা আগের দিন ক্লাসের পর আমি বোধহয় শেয়ার করেছি, দেখো একটু খেয়াল করো।
তার স্যার শীট 4 আর শীট 5 within next Thursday।
হ্যাঁ, মানে নেক্সট ওয়েডনেসডে আমাদের ডাইনামিক্সের ক্লাস হবে, তার সঙ্গে
সেটা স্যার পসিবল, ঠিক আছে?
হ্যাঁ ঠিক আছে।
শীট 4 তো স্যার সাবমিট করলাম।
হ্যাঁ শীট 4 করে দিয়েছি সাবমিট।
আরে ঠিক আছে না, মোটা কথা শীট 5টা নেক্সট থার্সডে মধ্যে করতে হবে।
ঠিক, শীট 4 শীট 5 সাবমিট করো, তারপরে একসঙ্গে চেক করব, ঠিক আছে?
ওকে স্যার।
and next Saturday we'll do sorry, by next Saturday I think we'll be done with dynamics as well. ঠিক আছে?
ঠিক আছে স্যার।
ঠিক আছে, তো shall we end our class here? আমি রেকর্ডিংটা শেয়ার করে দেবো, আর আমার সঙ্গে অ্যাটেন্ডেন্সটা তুমি শেয়ার করে দিও।
হ্যাঁ স্যার, করে দেবো।
ওকে ওকে